Okay, for number 91, now we have a common ion in solution. That's going to change the solubility due to the common ion effect and the Chatelier's principle. So number 91, you're still dealing with calcium phosphate. So we have a calcium phosphate solution, but instead of being alone, it is in the presence of a 0.20 molar sodium phosphate. If you have 0.20 molar sodium phosphate, which is a completely soluble salt, it will dissociate into 3 Na plus ions and 1 PO4 3 minus ion. So if the molarity of this is 0.20, this is 0.60, and this is 0.20. We don't care about this, we only care about the phosphate because we're dealing with calcium phosphate solution. So in a calcium phosphate solution, it's going to dissociate into 3 calcium ions and 2 phosphate ions. In this case, instead of both of these starting at 0, our phosphate ion solution starts at 0.20 molar. Calcium starts at 0, and then as this dissociates, this still goes up by 3x, and this goes up by 2x. So this becomes 3x at equilibrium, and this is 0.20 plus 2x. Because we're dealing with numbers so small and the k values are tiny, we can ignore this and call this 0.20. So our KSP value is calcium cubed times phosphate squared. So now we plug in the values that we know. The value for KSP for calcium phosphate is 1.3 times 10 to the negative 32. Our calcium ion concentration is 3x, and we cube it. And our phosphate concentration is 0.2, and it's going to be squared. So now when you plug all of that in, 1.3 times 10 to the negative 32 equals 27x to the third times 0.2 squared, which is 0.04, and then you solve for x. To solve for x, divide this 1.3 times 10 to the negative 32, divide by 27, divide by 0.04, and then take the cube root of that answer, and you should get 2.3 times 10 to the negative 11th, and that is now the molar solubility. And as you can tell from the last problem, the solubility has decreased because of the presence of the common ion.